Okay, welcome to the 2004 AP Calculus video where I'm going to be going over these questions and we'll look at how to solve them. So, in this first one, we have traffic flow defined as the rate in which cars pass through an intersection measured in cars per minute. So this function is measured in cars per minute, and then the traffic flow at a particular intersection is modeled by the function f, where f is measured in cars per minute and t is measured in minutes. Cool. Now let's see what they want. So to the nearest whole number, how many cars pass through the intersection over the 30-minute period? So to answer that, first let's look at what f of t is. So f of t is the number of cars passing through per minute at a certain time, right? So at, say, 5 minutes, you can plug in 5 into here and you figure out how many cars per minute is passing through the intersection at that time. Okay, so if we want to figure out how many cars are passing through the intersection over a 30-minute time period, we're adding up how many cars are passing through the intersection in the first minute, in the second minute, in the third minute, and yada yada yada. We're adding up all the different pieces, and we're also adding up the fractional times, right? Half a minute, 1.5 minutes. So when we're adding up an infinite number of times, and that's where integration comes in. So if we want to figure out how many cars are passing through the intersection over the 30-minute period, we're going to take this function and we're going to integrate it from 0 to 30. And that's going to add up all of those values and give us the total number of cars that pass through the intersection. Okay, so to figure this out, we're going to take this function and we're going to integrate it from 0 to 30. Okay, and then, so we'll be integrating f of t dt, and then since this is part of the calculator section of the test, the first 3 questions are calculator friendly, you can just plug this right into your calculator and you're going to get the answer of 2474, and then it's going to be cars, right? That's our units, cars. Alright, so for points, this is 3 points. 1 point for the correct limits, because we're going from the starting time 0 to the ending time 30, because it's 30 minutes. Another point for putting the f of t in the integrand, and then the third point for the correct final answer. Alright, part B now. Is the traffic flow increasing or decreasing at t equals 7? Give a reason for your answer. Okay, so now there's some keywords in this problem. In this part of the problem, there's increasing and decreasing, right? Those are some of the calculus key terms that you see a lot, and you should really know what they mean to help you solve these kind of questions easily. So when we're talking about increasing, we're talking about a positive f prime. Okay? And then when we're talking about a function decreasing, we're talking about a negative f prime, right? You should probably already know that walking into the test. So if we want to figure out is the traffic flow increasing or decreasing at t equals 7, we need to look at is the derivative positive or negative at t equals 7. So we'll be taking the derivative with respect to time at t equals 7 of f of t. Okay, and again, this is something that you do in your calculator. So once you do that, you will get that f prime of 7 is approximately equal to negative 1.873, and obviously that is less than 0. So since it is less than 0, the f prime is negative, so the function is decreasing. So the traffic flow is decreasing at t equals 7. Do you want a reason? So we'll say, okay, the traffic flow is decreasing at t equals 7 because f prime of 7 is less than 0. This was a 1-point question, 1 point for the correct answer with an explanation. Okay, part C. What is the average value of the traffic flow over the time interval from 10 to 15? Indicate units of measure. Okay, so when we're dealing with an average value of a function, you should know the average value formula. So the average value of a function from a to b is 1 over b minus a times the integral from a to b of f of t dt, or f of x dx, or whatever. So basically, this is our formula. We're going from t equals 10 to t equals 15. So all we got to do is replace. We'll replace a with 10, and we'll replace b with 15. Since we're starting at time t equals 10 and going until time t equals 15. The formula then becomes 1 over 15 minus 10 is 5, times the integral from 10 to 15 of f of t dt, and then you put that in your calculator, and we're going to get 81.999. So as for units, the average value of a traffic flow, the units for the average value of a function is the same as the units for the function. So since the units for the function is cars per minute, we can say that the units for the average value of the function is also cars per minute, like that. So that is our answer. And then for units, for points, we have 3 points. 1 point for including the correct limits on your integral, 10 and 15. 1 point for putting the right thing in the integral, and 1 point for the correct final answer. Okay, part D, finally, what is the average rate of change of the traffic flow over 10 to 15? Notice that these two are very similar in name, average value, average rate of change. I'm showing you. And when I took this class, I thought these two were the exact same thing until about like March or April. So yeah. So we want to find the average rate of change. The difference is if we're going to graph this function and say it looked like this, the average rate of change is just the slope from one point to the other point. It's just the slope. While the average value has to take into account the actual function and figure out what the average value of this function is along this whole path. So that's the quick summary. And average rate of change, so since it's just a slope between 2 points, we can use the slope formula for the function f. And that'll get us f of 15 minus f of 10 over 15 minus 10, which is, again, you can put this in the calculator, take this function, plug in 15, plug in 10, do all the math, and you'll get 1.518. And then as for units, okay? So we just found the slope, right? We just found the slope of, if we were to graph this, there'd be time on this axis, and then f of t on this axis, right? And there's this function. So when we're dealing with the slope of a function, the units are the units for the y-axis divided by the units for the x-axis. So the units for the y-axis, the units for f of t is cars per minute, right? So we'll have cars per minute, and then we're going to divide by the units for the x-axis. T is measured in minutes. Okay, so this is the units for the slope. Cars per minute, or as we more eloquently like to put it, cars per minute squared, like that. Okay, that's our final answer. So this was a 1 point question, just 1 point for the right answer. And then, so for both parts C and D, if you included the right units, that would net you an extra point. Okay, that was the end of question 1. Let's move on to question 2. Okay, question 2. So we have f and g are functions. F of x is 2x times 1 minus x, and g of x is 3 times x minus 1 times square root of x. For 0 is less than or equal to x is less than or equal to 1. The graphs of f and g are shown in the figure to your right. Part A, find the area of the shaded region enclosed by the graphs of f and g. Okay, so where we're going to approach this is we want to figure out the area of this region here, right? This gray shaded region. So let's think about if we were to integrate from 0 to 1 of f of x, right? That integral would give us the area under f of x, which is this region. Okay? And then if we were to integrate from 0 to 1 of g of x, and of course this is dx on both these, that would get us this purple region, because that's the area under the curve for g of x. That's this region, and this is f of x. So what do we do to get the total area? Well, your first instinct might be to add these, but think a little bit more carefully, okay? Because g of x is a negative value, right? G of x is under the x-axis, so this integral is a negative number. But we want the total area, which means we want to take the absolute value of this and the absolute value of this and add those together, right? Now you could do that by just putting absolute value signs on the outside. That would do the trick. Or instead of adding them, you can subtract them. Because it's kind of like subtracting a negative is like adding, right? So we're taking a positive number and we're subtracting a negative number, which will give us a net positive of this. Right? If we wanted to combine this into one integral, we could take this and just combine f of x and g of x into one integral, f of x minus g of x dx. And then if this were to go into your calculator, plug in this for f of x, plug in this for g of x, put that in their integral, and you'll get 1.133. This is a 2-point question, 1 point for writing this integral expression, and 1 point for the final answer. So part B, find the volume of the solid generated when the shaded region enclosed by the graphs of f and g is revolved around the horizontal line y equals 2. Okay, so we'll start by sketching y equals 2. It's not going to be obviously to scale, but just for the sake of keeping it on the white space, I'm going to pretend it's right there. So we'll say that is y equals 2. Okay, so now the first step for these kind of problems, where we're rotating a region around another line, is to find the radii. And the radii are basically the distance from this line to each of the curves. There are two curves here, f of x and g of x. We want to find the distance from this line to each of those two curves. So this would be the first distance here in blue, and then this would be the second distance here in red. Okay, and obviously these are not constant values, these are not numbers, these are functions as a function of x, because as you move over, the values of these radii change. Okay, so we need to find these expressions for the radii in terms of x now. That's the next step. So I'll call this a lowercase r, it's a small radius. I'll call this uppercase r for a big radius. Okay, so let's figure out how to find an expression for this little radius. So this total distance from y equals 2 to the x-axis, this entire distance is the constant value of 2, right? Constant value of 2. And then from here upwards, from the x-axis to the curve, this distance is f of x. Okay? This distance is f of x, and this total distance is 2. The blue line is the difference between those two things. It's what you get if you take the total distance and you subtract out f of x. This blue is what's left over, essentially. So the way you get blue is you start with 2, which is the total distance, and then you're taking out f of x. And then the radius is what is left over. I'm just going to make this look a little bit better. Okay, so we can do the same thought process for the large, that's the wrong color, the large radius, big R. So we have our starting distance 2, and then remember g of x is negative, right? So I'm going to subtract g of x because I'm subtracting a negative number, so that's going to give me the sum of the 2 and this g of x portion here, right? This negative g of x, this is a positive because g of x is negative. So 2 minus g of x, that's the total distance of this radius there. So now that we've identified these two radii, you can plug in these two functions for f of x and g of x if you want. I'm just not going to do it to save time. So now that we've figured those two out, we can just plug them into our equation and we're good to go. So we did the hard part already. So the equation for this is times the definite integral from a to b, I'll get to a and b in a second, of big R squared minus little r squared dx. So a and b are the x values of your starting and ending points. So you're starting at x equals 0, and you're going until x equals 1, right? You're starting at 0, ending in 1. So these are your limits for your integration. You're not going any further than that. So in this case, a would be 0. So my eraser. A equals 0, and then b would be 1. Alright, so you can take this 2 minus g of x and 2 minus f of x, you can plug that into here. I'll even do it for you just to show what it would look like. Pi times the integral from 0 to 1 of 2 minus g of x. What's g of x? Okay, 3 times x minus 1 times square root of x squared. That's our big R. That's 2 minus g of x squared. That's our big R squared. And then from that, we're subtracting little r squared. So 2 minus f of x, which is that 2x times 1 minus x squared. So this is pi times the integral from 0 to 1 of big R squared minus little r squared. That's just this formula. We plugged in our values of big R and little r, and then dx. So if you put this stuff in your calculator, you would get that it is equal to 16.179. Okay, that's our answer. And then as for points, this is a 3-point question. 1 point for including the pi and the limits of 0 and 1. 2 points for this big guy here, big integrand. And then 1 point for the final answer. Did I say it was 3 points? I might have said it was 3 points. It's 4 points. Yeah, okay, so now we'll move on to part C. Okay, so part C. Let h be the function given by h of x equals kx times 1 minus x. For 0 is less than equal to x is less than equal to 1. For each k is greater than 0, the region enclosed by h and g is the base of a solid with square cross-sections perpendicular to the x-axis. This value of k for which the volume of this solid is equal to 15. Write but don't solve an equation involving an integral expression that could be used to find the value of k. Wow, that's a big chunk of text. Let's look at this a bit more carefully, shall we? So h is this function given by h of x is kx times 1 minus x, okay? And then for each k is greater than 0, there's a region enclosed by the graphs of h and g. So now what's happening is we're just ignoring f of x, and there's this other function f that's kind of taking its place. Notice the similarities between h of x and f of x, okay? And also notice some key things about h of x. Let's take a deep dive and look at h of x for a second. H of x, right? Notice that, like f of x, h of 1 equals 0, because if you plug in 1 into here, it would be 1 minus 1, so that'll make h of x 0. So h of 1 is 0, so it's going to look something like this, because h of 0 is also 0, because if you plug in 0 here, that'll make this whole thing 0. So it's all h of x is also going to start here and here. And then notice also, just like f of x, when we're going from an x that's between 0 and 1, h of x is going to be positive. Since k is positive, and then the rest of it is always going to be positive for an x between 0 and 1, we also know that h of x is positive for 0 is less than or equal to x is less than or equal to 1. Right? Less than or equal to 0, rather. So yeah, so these are some things that we've noticed about h of x, right? So it's going to look very similar to f of x, but it might be a little bit under like that, or it might be a little bit over like that, but it's going to look very similar. Okay, so now what are we doing? So we have this region h, and we're drawing square cross sections, right? So what's going to be the length of those cross sections? It's going to be, like, for example, this is going to be one cross section. This is going to be one square cross section. This is going to be another square cross section. This is going to be another square cross section. And so we have a bunch of different square cross sections. And then let's find an expression for those cross sections first, okay? So we know that h of x is going to look kind of like f of x. So I'm just going to leave this here to make our lives easier. We'll just pretend that this is h of x, okay? So this this region that we want to, like the base of this square that we're going to use to integrate later on, that's this distance, right? That's going to be this distance from h of x to the x-axis plus this distance from the x-axis to g of x. Okay, that's going to be h of x plus this distance. And remember, it's negative, so we're going to subtract it. H of x minus g of x. Okay, and then that gives you the length of that side, right? The length of that base that we're using as the base of a square, as one of the sides of a square. And then, so what's dealing with squares, the area of the square, so the area of this square, that's a different color, isn't it? Yeah, it is. The area of this square is going to be the side squared. So we'll take the side length and we will square it, okay? And this, for any x value, this will give us the area of a square with this being the base for that x value, okay? And then, so since we're dealing with, adding up all these infinite squares from 0 to 1, we're going to be integrating this from 0 to 1, right? And I'll put a dx on the end because it's an integral now. So this is going to give us the total area from 0 to 1 of all of these infinite squares being added up, the total volume of that region, the three-dimensional region. Okay, so now let's take this and we'll plug in values for h of x and g of x. Okay, so we're going from, I'll just rewrite that here just for ease of reference. Okay, so we can take h of x. What is h of x again? Kx times 1 minus x. So kx times 1 minus x, and then minus g of x. G of x is 3 times x minus 1 times square root of x. And we're taking this whole thing, and we're squaring it and putting a dx on the end. So this expression here, where k is a constant and then x is the variable that we're integrating by, that's going to give us, like we said before, this total region of all the rectangles being added up, or all the squares being added up, sorry. So we're saying that for some value k, this integral here is equal to 15. There's some value k for which, if we take this integral, we'll get 15, right? They're not asking us to find what that value is, they're just asking us to write the expression that we could use to solve it. Okay, so that means we're done, right? We could take this integral expression, if we wanted to, we'd solve this, and we'd get the value of k. So for points, this is a 3-point question. 2 points for the main big boy stuff in the integral, and then 1 point for everything else. So the limits and the setting it equal to 15 part. Okay, that was the end of question 2. Let's look at question 3. Okay, question 3. In the question we have a particle that's moving along the y-axis. So its velocity for positive time is given by that. And then at time t equals 0, the particle is at y equals 1. So that's its initial position. And then tangent to -1, that's arctan, not 1 over tan. Okay, so now let's look at the problem. Part A, we need to find the acceleration of the particle at time t equals 2. Okay, so since they're giving us the velocity and they're asking us for acceleration, we should try to think of the connection that's between velocity and acceleration. So the connection is that if we have the acceleration at a time, that's equal to the derivative of the velocity at that time. So a of x is equal to v prime of x, so a of 2 is equal to v prime of 2. Okay, so because we want to find the acceleration at time t equals 2. So since we know the velocity function, we can just take the derivative of the velocity function, which is 1 minus the inverse tangent of e to the t, like that. And then we can evaluate this at t equals 2. And if we put this whole thing in our calculator, we will get negative 0.133, which is our answer, because that's v prime, which is the acceleration at time t equals 2. This was a quick 1-point question. Part B, is the speed of the particle increasing or decreasing at time t equals 2? Give a reason for your answer. Okay, so when we look at speed, the first thing that should come to your mind, pretty much always when they're asking about speed, what they're gonna want you to look at is the sign of the velocity and the acceleration. Okay, so here's how speed works. If the acceleration and the velocity have the same sign, then the particle is speeding up. Its speed is increasing. If the velocity and acceleration have opposite signs, then the particle is slowing down, so its speed is decreasing. So if we want to figure out if the particle is increasing or decreasing speed, we need to look at the sign of the velocity and the acceleration. Okay, we already found out in part A that the acceleration at time 2 is negative 0.133, which is obviously less than 0, so acceleration is negative. If the velocity is negative, then the acceleration and velocity have the same sign, so the particle is speeding up, even though they're negative. If the velocity is positive, then the acceleration and the velocity will have opposite signs, then the particle will be slowing down. So if we just find v of 2 by plugging 2 into the velocity expression, we will get negative 0.436, which is, again, less than 0. So what have we determined now? We've determined that the acceleration and the velocity have the same sign at time t equals 2. So for our explanation, I will say, since the velocity and the acceleration have the same sign at t equals 2, the speed is increasing. And what I'd recommend you do is, instead of saying a of 2, I'd recommend you say v prime of 2, since those are the same thing, because it's better to give it's better to give your answer in terms of the functions they give you. So instead of saying a, you can say v prime. Okay, so this was again a 1-point question. Okay, part C now. Find the time for a positive t value at which the particle reaches its highest point. Justify your answer. Okay, so when it reaches the highest point, that is going to be when its position is the maximum, right? That's when it's going to be at its highest point. It has a maximum position. So we want to find when the particle has a maximum position. Okay, and then how do we figure that out? Well, if we want to figure out the maximum of a function, we take its derivative and set it equal to 0, right? By the first derivative test. So what we can do is we can take the derivative of position and set it equal to 0. So what is the derivative of position? Well, the derivative of position is velocity, right? So to figure out where the position is at a maximum, we can take the velocity function, which is the derivative of the position function, and set it equal to 0. So what we'll do is we'll take the velocity function, which is 1 minus the inverse tangent of e to the t, and we'll set that equal to 0. And then now we can solve this for t. I'll add the inverse tangent of e to the t to both sides. That'll get us that the inverse tangent of e to the t is equal to 1. And now what you're going to do is just plug this into your calculator, in your graphing calculator, where this will be y1, this will be y2. You can graph it and then find the intersection point, and that'll be your t value. And if you do that, you will get that t is approximately equal to 0.443, okay? So this is really just a candidate point to make sure that it's the actual maximum. What we'll do is we'll use a little thing like this, of a number line sort of. We'll take 0.443, which is our 0, and then we'll test a point that's greater than this, and we'll test a point that's less than this. But remember, the point that's less than this, it still has to be greater than 0 because we want a positive time value. So if I test a random number that's in between 0 and 0.443, I need to check that whether it's positive or negative. So let's say I take like 0.1 or 0.2 or whatever and I test it in the velocity function. I'm going to get that the answer comes out as positive. Then if I test any number that's greater than 0.443, I'll find out that the answer comes out negative. Okay, so what does that mean? Well, it means that initially the position is increasing, and then the position is increasing, and then it's decreasing. So at this point, at 0.443, the position is at a maximum, right? So when it goes from increasing to decreasing, that means we have a maximum position. So this is, we've checked it and it does check out. This is where it's reached its maximum position. So we'll say, well, the particle reaches its highest point at t equals 0.443. This is sort of your justification, as it were. So this was a 3-point question. 1 point for recognizing that you need to set the velocity equal to 0. Another point for finding the time value where the velocity does equal 0. And then a third point for checking it and giving a proper explanation, the justification. Okay, part D. Find the position of the particle at time t equals 2. And then is the particle moving toward the origin or away from the origin at time t equals 2? Justify your answer. Okay, so before we get into this, I'm going to quickly remind you of the fundamental theorem of calculus, because we're going to use that to solve this problem. So the fundamental theorem of calculus, also known as the FTC, basically says that if we're integrating from a to b f prime of x dx, this is equal to f of b minus f of a. Okay, fundamental theorem of calculus says that this is true. So we're going to use this to help us solve this problem. If you couldn't get it right away, take this as a hint and try one more time. So okay, let's look at the answer now. We're gonna say that our position function, because we're trying to find the position of the particle, right? So we're gonna define the position function. I'll say let, I don't know, y of t, because we're dealing with the y-axis, be the position. Okay. So we have y of t being the position function, and then so noticing that since the derivative of the position function is the velocity, we can go backwards and say that the integral of the velocity function is the position. So if I were to integrate the velocity function v of t dt, this would be equal to the position function y of t, right? Since v of t is the same as y prime of t, and that would, So now if I were to put bounds on this integral from a to b, then I could say, all right, this is y of b minus y of a. Okay, so now we're going to go up and use this crucial piece of information that you needed to see here, right here. At time t equals 0, the particle is at y equals -1. So when they give you that information about the position, we're going to set t equals 0 to be one of the bounds of this integral. So I'll let it to be this bound here. 0, okay? And then since we want to find the position at time t equals 2, I'll set the other bound to be 2. And if it doesn't completely make sense why I'm doing this right now, you'll see in a second. So if I were to do this out, according to the fundamental theorem of calculus, we will get y of 2 minus y of 0. Okay? And then here's the fun thing now. This is what we want to find, right? This is something we want. We want y of 2, right? But look at this, y of 0. We already know y of 0, right? They said it's -1. So this we know already. And then the integral from 0 to 2 of the velocity, we can figure that out, right? We have the velocity function. We can put it in a calculator and integrate it. So this is also something that we know. Now that we know this, so if we calculate numerical values for this and this, that'll allow us to figure out y of 2, right? So if I were to solve this for y of 2, I'll get that y of 2 equals y of 0 plus the integral from 0 to 2 of v of t dt. Okay, so if we just put the v of t part in the calculator, we'll find that the integral from 0 to 2 of the velocity function equals negative 0.361, right? And then remember that y of 0 is negative 1, right? From up here, at time t equals 0, the particle at y equals negative 1. So that allows us to say that at time t equals 2, y of 2 is equal to negative 1, y of 0, and then instead of saying plus a negative, we'll just say minus 0.361, right? This is y of 0, this is the integral. So we have successfully found the position at time t equals 2, and they asked us for one more thing, didn't they? They asked us, is the particle moving toward the origin or away from the origin at time t equals 2? Okay, so to figure that out, let's think about this. So I'm going to say like we have the axis here, that the particle is moving on the y-axis, and I'll say this is the origin, right? If the particle were moving away from the origin, right, one of two things is happening. One, the particle could be moving in a positive direction. It could be moving in a positive direction, and it's starting in a positive position. So it starts at a positive position and goes more positive. Or the alternative is, it could start in a negative position, and it could go more negative. If it was starting in a negative position and moving more positive, for example, it would be moving toward the origin, right? So we're noticing that if the particle is moving away from the origin, then the velocity and the position have the same sign, right? So if we figure out the sign of the velocity and the sign of the position, we can determine whether or not the particle is moving away from the origin. Okay, so we'll look at v of 2, and we'll look at y of 2. That's not a 2. Y of 2. Okay, so v of 2. If you remember all the way back from part B, where we found v of 2 to determine the speed, you'll remember that it came out to be negative 0.436. Obviously, if you didn't erase everything like I'm doing, you would have just been able to see it. And then the position at time t equals 2, we determined that it's this negative, I'll just simplify that to negative 1.361. And notice that these both have the same sign, right? They're both negative. So we're dealing with this bottom scenario here, where it starts at a negative position and it moves more negative. So it is moving away from the origin. Okay, so for our explanation, we'd say, well, since v of 2 and y of 2 have the same sign, the particle is moving away from the origin. That would be our justification. Okay, so for points, this is a 4-point question. 1 point for setting y of 0 equal to negative 1 that we noticed in the problem. Another point for calculating the value of the integral from 0 to 2 of the velocity. A third point for getting the correct answer for the position function. And then a fourth point for a correct justification of the particle moving away from the origin. Okay, now that was the end of question 3. Let's move on to question number 4. Alright, so question 4. We have to consider a curve given by x squared plus 4y squared equals 7 plus 3xy. And then in part A, we need to show that dy dx is equal to this. Okay, so they're giving us the answer for what the derivative is. We just need to show that this is what it's equal to. So they're kind of helping us out a lot here, right? What we're going to do now is we're going to first take the derivative of this using implicit differentiation, since there are x's and y's all mingled up together and not in a nice neat format like we sometimes have. So when we're differentiating this function, I'll rewrite the function again real quick. X squared plus 4y squared equals 7 plus 3xy. Okay, so we'll differentiate this whole thing with respect to x. Alright, so we'll start with x squared. Using the power rule, we'll get 2x. And then for the 4y squared, using the power rule again, we'll get 8y. But since we're differentiating with respect to x, not with y, we need to add a dy dx on the end by the chain rule. Okay, and this is equal to 7, the derivative of 7 is 0, plus 3xy. Okay, so for the 3xy, since there are two things being multiplied together, we're going to use the product rule. First, I'll leave the 3x, and then take the derivative of y, which is dy dx, and then I'll add 3y times the derivative of x, which is 1. So this is it. This is our derivative. If you were hesitant on that part, I'd go and review those kind of things. So now that we got the derivative, for the next step is going to be to isolate dy dx. So I'm going to bring everything that has a dy dx next to it, I'll bring it onto the left, and everything else is going to move on to the right. So if we do that, and all the dy dx's are going to be on the left, okay, so this guy is going to come over onto the left side and hang out here. And then everything else is going to be on the right. 3y minus 2x, right? This guy over there. So now, since there is a dy dx here, and a dy dx here, I can factor it out, and I'll get dy dx times x, okay, times 8y minus 3x, so that's factored out, equals 3y minus 2x, and then now it's just a matter of bringing this thing over to the bottom. So dy dx equals 3y minus 2x over 8y minus 3x. Okay, so that's our final answer. We solved for dy dx. Let's just make sure that's what they gave us. 3y minus 2x, 8y minus 3x. 3y 2x, 8y 3x. Okay, we're good. Did that. So this was 2 points. 1 point for actually performing the implicit differentiation, and then another point for getting the right answer for dy dx and showing that those are equal. Okay, part B. Show that there's a point P with x coordinate 3 at which the line tangent to the curve at P is horizontal. Okay, so if we're doing this, so the line tangent to the curve at P is horizontal. What is the line tangent to the curve? That's the derivative, right? And it's horizontal, meaning the slope is 0. So there should be some point along P where the derivative is equal to 0 and the x-coordinate is 3, right? So if we're doing that, okay, so we'll take the derivative and set it equal to 0, because this is when the line tangent to the curve is horizontal. The slope is 0. Okay? So if we want to say this is equal to 0, we'll take this entire thing, 3y minus 2x over 8y minus 3x, and say, okay, this has to be equal to 0 if the derivative is 0. And remember, if the fraction is equal to 0, then its numerator is equal to 0, right? There's no other way. So we can just kind of ignore this bottom part and just focus on the top. 3y minus 2x is equal to 0, or 3y is equal to 2x, whatever. But we can also notice that the x-coordinate is 3, right? So I can plug in 3 into here. That'll give me 3y minus 2 times 3 is equal to 0. And then if I solve this for y, I'll add 6 to both sides, divided by 3. Y is equal to 2. So x equals 3, y equals 2. This is our point 3, comma 2. Okay, and then that's what we wanted to show, right? We want to show that there's a point P with x-coordinate 3 where the derivative is 0, where the line is horizontal. And we found the y-coordinate of P. So one more thing we want to do, just to be sure that this is our answer, is we want to check that P is actually on the curve. Because this is great and all, but this is where the derivative is 0. But if the point isn't actually on the curve, then it's kind of useless, right? So we'll take 3, 2, and we plug it into the actual function and make sure that it checks out. Okay, so we'll get x squared, 3 squared, plus 4 y squared equals 7 plus 3x y. So 9 plus 4 times 4 is 16, equals 7 plus 3 times 3 is 9, 9 times 2 is 18, 9 plus 16 is 25, and then 7 plus 18 is also 25. So that checks out. So the point 3, 2 is on curve. Okay, so then we can now finally say that 3, 2 is the final answer. Right, that is the point P that we're talking about. So as for points, this is a 3-point question. 1 point for recognizing that you need to set the derivative equal to 0. Another point for finding the point 3, 2. And then a third point for checking that it is on the curve. Alright, so part C. Find the value of d squared y over dx squared, its second derivative, at the point P, found in part B. So I wrote that here. Does the curve have a local minimum, local maximum, minimum on either point P? Justify your answer. Okay, so this is a part where the algebra is going to get a little bit messy. So this is the reason you need strong algebra skills in this class, not just calculus. Okay, so to find the second derivative, we're going to take so we're going to use the quotient rule here since we have something on the top and something on the bottom. So we'll have the bottom times the derivative of the top. So 8y minus 3x times the derivative of the top. The derivative of the top is 3y. Oh wait, no. It's only not 3y. 3. dy dx minus, and that is the derivative of that is 2 minus, and then we have the top, which is 3y minus 2x times the derivative of the bottom, which is 8 dy dx minus the derivative of 3x is 3 over the bottom, which is 8y minus 3x squared. Okay? So this is the second derivative. And then now to figure out what the derivative is at point 3, 2, we need to plug in 3, 2 into here. And one thing to notice to deal with these dy dx's and make this problem slightly more manageable, remember that at point 3, 2, the derivative is 0, right? That was what we wanted to do with point P. We wanted to find out where is the derivative 0. So whenever we see a dy dx, we can replace it with 0. I'll write that down. Here, dy dx equals 0 when we're at the point 3, 2. Okay? So let's plug in some numbers. D squared y, or second derivative, again, I don't know why I keep saying like that. We have 8 times 2 minus 3 times 3. That's the first part. And we're multiplying it by 3 times 0 minus 2 minus, okay, well, 3 times 2 minus 2 times 3. And then notice that this is just 0 anyways, right? 6 minus 6. So whatever this part is, it doesn't even matter. This whole thing just goes out to 0. And we're dividing it by 8y minus 3x, which is 8 times 2 minus 3 times 3 squared. That's the bottom part squared. So now we just plugged in the numbers, and you can evaluate this just a tiny bit more, just to make our life a little bit easier. You could just leave it here, but as you'll see in a moment, it'll be helpful for us to have this simplified just a tiny bit more to help us more clearly see what's going on here. I can just write this as 16 minus 9 times negative 2 over 16 minus 9 squared. I think that's a nice place to leave it off. Okay? And they also asked us one more thing. Also asked us, does the curve have a local maximum, a local minimum, and neither at point P? Okay, so to do this, we're going to use the second derivative test. Okay, remember, the second derivative test says that if the first derivative is 0 and the second derivative is greater than 0, then there's local minimum. If the first derivative is 0 and the second derivative is less than 0, then it's a local maximum. If they're both 0, then there's no conclusion. So to figure out whether the point has a local maximum or minimum, we can use the second derivative test. We know the first derivative is 0, right? So we can figure out the second derivative and see if it's greater than 0, then we have a local minimum. If it's less than 0, we have a local maximum. And this seems to be a positive number times a negative number divided by a positive number. So the second derivative is negative. So to recap, we know that dy dx equals 0, and then the second derivative is less than 0. So because of these things, we know that there is a local maximum by the second derivative test. So our explanation would say, at point P, dy dx is 0, d squared y over dx squared is less than 0, therefore there is a local maximum at point P. That was all they asked for, I believe. Yeah, the justified answer. Yeah, so okay, point, this is 3 points. 1 for doing the second derivative, 1 for evaluating it at point 3, 2, and another for your explanation that there's local maximum at point P. That was the end of question 4. Moving on to question 5. For question 5, so the graph of the function f, shown here, consists of a semicircle and 1, 2, 3 line segments. Let g be the function given by this here. In part A, we're asked to find g of 0 and g prime of 0. Alright, so what we'll do is we'll just plug in 0 in for x and see what happens, right? So g of 0 is going to be the integral from negative 3 to 0 of f of t d t. Okay. So let me just sketch that out here. So we're starting at negative 3, like that, and we're going to 0, like that. So this is the area, or this is the region that we want to find the area of. Easy enough, right? This, what is this called? Trapezoid? Yeah, trapezoid. So we'll split this up into a triangle and a rectangle. This triangle has one side 3, other side 1, total area 3. This is half of that other rectangle, this triangle. So since it's half of it, it's going to have area 3 halves. Or you can do 1/2 base height if you want. Okay, so if we want to figure out the total area, so it's going to be the rectangle plus the triangle. That's 3 plus 3 halves. That's the total net area under the curve. And that's g of 0. Next, that's the integral from negative 3 to 0. And then g prime of 0, right? So to figure out that, we'll look at g prime of x. So to find g prime of x, we want to take this whole function and take the derivative with respect to x, right? So if I want to take the derivative, and I'll get g prime of x, that's equal to, that's going to be equal to the derivative of this guy with respect to x. So d dx times that integral, that accumulation function. And then according to the fundamental theorem of calculus, in addition to what we said in question 3, the fundamental theorem of calculus also tells us that this guy here is equal to just f of x. We're taking the derivative of the accumulation function with x is one of the bounds of the integral, that this whole thing just comes out to be f of x. So basically, to summarize, g prime of x equals f of x. And by the way, whenever they give you an accumulation function in a problem, this is like pretty much almost like guaranteed they're going to ask you to do this step, so make sure you know how to do it. So now that we've figured out that g prime of x is f of x, since they asked us for g prime of 0, that's equal to f of 0. And f of 0, if we look on our graph, is equal to 1. So 1. That's it. This is one point here finding g of 0. This is another point for g prime of 0. Okay, so part B, we need to find all values of x in the open interval -5 to 4, where g attains a relative maximum. Justify your answer. Okay, so to do this, what I like to do is I like to start out with what I want to find, right? Where g attains a relative maximum, and then I need to look at what I know. I know a lot about the graph of f, right? So what I want to do now is I'm going to start with what I want to find and try to link it to what I know. I'm gonna write down concrete steps where I connect G to something else and then something else, and then eventually connect it to F. So my end goal is being connecting G to F to try to figure out what I can do with F to tell me when G attains a relative maximum. If that doesn't make sense, I'll show you what I mean in a second. So to figure out where G attains a relative maximum, so where G has a relative maximum, what does that mean? Well, when G has a relative maximum, that means that the derivative switches from positive to negative, right? This is one example of a concrete step that I'm taking. And then how can I connect this to F? Well, I know that, remember from part A, we said that G prime of x is equal to f of x. So I can make another concrete step and I can say f of x switches from plus to minus, positive, negative. Another benefit of doing this is it really helps your grader for your AP exam see exactly what you're thinking in your head when you're trying to solve this. So we said that G is relative maximum, so f switches from positive to negative. So now we've completed our task. We've looked at what we know. What we know is f of x. What we want to find, and we've connected those two. So when G has a relative maximum, then f of x switches from positive to negative. So I can find all the places where f switches from positive to negative, and that's going to be where G has a relative maximum. Okay, so let's look at this here. If we look at this, we'll say, okay, so here it switches from negative to positive, and then for this whole rest of the path it stays positive, and then here it switches from positive to negative, right? So that's a point right there. And then it goes on and on, and that's it. So this is the only point where f of x switches from positive to negative. So if we go back up our train of thought here, that's where G has a relative maximum. This occurs at x equals 1, 2, 3, x equals 3. So G has a relative maximum at x equals 3. And if you want to write it out, you can say G has a relative maximum at x equals 3 because G prime of x switches from positive to negative at x equals 3. Remember in your explanation, if you can, try to include only functions that they give you, unless you really have to do something else. So this was a 2-point question. 1 point for correctly figuring out x equals 3 as your only answer, and another point for a correct justification. Part C, find the absolute minimum value of G on the closed interval -5 to 4. Justify your answer. Okay, so when we're dealing with absolute minimum problems, the step that I like to do first is to make a list of all the candidate points. Wrong call. I like to make a list of all the candidate points. Okay, let's see what we got. So whenever you're dealing with absolute extrema, two of your candidate points are always going to be your endpoints. So x equals -5 is a candidate point, x equals 4 is a candidate point. In addition, more candidate points are going to be, if you're dealing with the absolute minimum, then your candidate points are your relative minimum. If you want to find the absolute maximum, more candidate points are your relative maximum. So since we want to find the absolute minimum, we need to also look for the relative minimum to put as our candidate points. Okay, so to figure out where G has a relative minimum, if we follow the same thought process that we followed in part B, we can find out that G attains a relative minimum where it switches from negative to positive, right? So that's going to be right here. Similar to how here it switched from positive to negative, so we knew that this was a relative maximum. We can say here it switches from negative to positive, so here it's a relative minimum. So this is at x equals -1, -2, -3, -4. This is at x equals -4. So these three are our candidate points for where G has an absolute minimum. So now what we're going to do is we're going to take each of these values and actually calculate them for G. G of -5, G of +4, and G of -4, and find which one is the smallest. That's going to be our absolute minimum. Okay, so to start off with -5, if I plug -5 into x, I'll get the integral from -3 to -5 of f of t dt. And I'm not even going to bother switching the bounds, because I noticed right away that if I were to take the integral from -5, which is here, to -3, which is here, it's two triangular regions, which are opposite in sign, so they're going to cancel out, and my net area is going to be 0. So we can already say right now that this is equal to 0. And then next, g of 4. Notice that if I take the integral from -3 all the way to 4, the answer is obviously going to be a positive number, right? Because there's all of this positive area here, and then only this tiny negative area. So the net area is obviously positive, so this g of 4 is obviously going to be something that is greater than 0. And since we want to find the absolute minimum, this can't be the absolute minimum, because we already know that g of -5 is equal to 0. So g of 4 is crossed out. That's not possible. Finally, we have g of -4. Okay, so to find g of -4, we will take the integral from -3 to -4 of f of t dt. This time I will switch the bounds. Remember, if you're switching the bounds of an integral, you just stick a negative sign in the front, and you're all good to go. -4 to -3 of f of t dt. And so that's going to be from -4 to -3 is this triangular region, which is 1/2 times 3. So that is, oh wait, no, it's not that. It's 1/2 times 1 times 2, because the height is 2 and the base is 1. So this is negative of 1/2 times 1 times 2, which is going to be -1. Right? So notice that of these three candidate points, -1 is the smallest, right? So this is the absolute minimum. Okay, so the absolute min is -1. Notice again that they asked for the absolute minimum value. They didn't ask for the x coordinate, they asked for the actual value. So you wouldn't give -4, you'd give -1, because that's the actual value that it is. And then to justify your answer, we can, this is our justification. We're showing all the candidate points and showing why this is the only one that satisfies what we want. So this was 3 points. 1 point for identifying g of -4 as a possible option. Another point for actually finding out that g of 4 is the absolute minimum. And then another point for the explanation that why -1 is the minimum value of g of x. Part D, find all values of x in the open interval -5 to 4, at which the graph of g has a point of inflection. Okay, so like we did in part B, we're going to go through that kind of step-by-step logical reasoning process here. So we want to figure out where g has a point of inflection, right? G has point of inflection. So what does that mean? Well, it means that the derivative switches direction. Right? It switches from increasing to decreasing or decreasing to increasing. G prime switches direction. That's what a point of inflection is. So since G prime is again equal to F, we can say this is the same as F switching direction. F switches direction. So when we have when G has a point of inflection, F switches direction. So we can look at the graph of X or the graph of F and find out where it switches direction. Okay, so let's see. Here it goes up and it goes down. So here's a switch in direction. Down, 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 down. So here it goes down, and then here it goes up. Another switch in direction. And then here it goes up and then goes down. So here's a third switch in direction. So these are all the points with which is direction. So those are all the points where g has an inflection point. So they want the x values. So we'll have x equals -3, x equals +1, and x equals +2, like that. This was a 2-point question. You got 2 points for finding these 3 values, and you lost a point for any one you got wrong or you found an extra point. Yeah, that was it for question number 5. Let's move on to the final question, 6. Okay, question 6. Thankfully, the AP overlords decided that since it's at the end of the test, they're going to make this question pretty easy for you guys. So we have the differential equation, dy dx equals x squared times y minus 1. Part A, on the axis provided, sketch a slope field for the differential equation at the 12 points indicated. Alright, so we need to sketch a slope field for this differential equation. If you don't remember what a slope field is, it's basically just like a sketch of all the slopes at the different points. So you use the differential equation to get the slopes, because remember a derivative is a slope at a point, and you use that slope and just kind of sketch it on each of these dots, okay? So let's notice first that if x is 0, then the derivative is 0, right? So anywhere x is 0, this derivative is 0, it's a flat line. So I can go and for all these 4 points where x is 0, I can draw a flat line, like that. Okay? And then notice also that, whenever y is 1, it's also going to be a flat line, because the derivative is still going to be 0. Okay? So that leaves these other 6 points. And we also can notice that whatever it is on this side of the x-axis, or of the y-axis, on the opposite side it's going to be the same, because the x is being squared, and -1 squared is the same as +1 squared. Okay, so let's do this point, and we'll just copy that over there, and the same thing for these two. Okay, so we'll start with 1, 0. If you plug in 1, 0 in here, we'll get 1 times -1, which is -1. So the slope there is going to be -1, like that. And then I can just move that over there. And then over here, this is 1, 2. That's going to be 1 times 2 minus 1, so it's going to be +1. I have a slope of +1, like that. And then finally here, this is 1, 3. It's going to be 1 times 3 minus 1, so it's a +2 slope. It's going to be a lot steeper than the other one, like that. Okay, so this is the slope field for that differential equation, and this is worth 2 points. 1 point for the all these flat parts here, where the slope is 0, and then you get 1 point for everything else, so a total of 2 points. Okay, part B. So while the slope field in part A is drawn on only 12 points, it is defined at every point in the xy plane. Describe all points in the xy plane for which the slopes are positive. Alright, so slopes are positive. So if the slope is positive, remembering that the slope is just the derivative, if the slope is positive, the derivative is positive. So we want to make sure that x squared times y minus 1 is positive, it's greater than 0. So if this is true, one of two things is happening here. Either x squared and y minus 1 are both positive, and we have a positive times a positive, or they're both negative, so we have a negative times a negative, which makes a positive. However, since this is something being squared, this is always going to be either 0 or positive, right? So this can never be negative. So we'll never have the option of having a negative times a negative. So we only have a positive times a positive, which means that we'll have x squared being greater than 0, and y minus 1 being greater than 0, and y minus 1 being greater than 0. So if these are both true, then the slope is going to be greater than 0. So if we solve these, here we'll get y is greater than 1. Here we'll get x is not equal to 0, because remember, any value of x that's not 0 is going to be squared, will turn into a positive number. The only time this is not true, where we'll get x is 0 and 0 squared is 0, and obviously 0 is not greater than 0. So we have x is not equal to 0, and y is greater than 1. So this is these are the restrictions for where the slope is positive. Cool. So this was 1 point for getting the right answer. Okay, part C. Find the particular solution y equals f of x to the given differential equation with the initial condition f of 0 equals 3. And you've noticed I've erased the slope field just to make more space. Okay, so to solve this differential equation, what we have to do first is to bring all the x's on one side and the y's on one side. So we'll bring the y's on the left and the x's on the right. That's going to give us 1 over y minus 1 dy. I took this y minus 1 and brought it over to the left, equals x squared dx, right? I took this dx and brought it over here. I just rearranged this in this form. Okay, so now that we got all the y's on one side and all the x's on one side, to get rid of the d's, we can just integrate this, like so. We'll perform two separate indefinite integrals. So to perform this one on the left, you can technically use a u substitution, but since the coefficient with the y term is 1, we can just imagine like there's nothing really there, and this will just get us the natural log of the absolute value of y minus 1 like that. If it makes you uncomfortable to do that, and you're not sure when to use it, go ahead and use the u sub, but the general rule is if there's no coefficient to the y term, go ahead and just imagine it's just y. Okay, so this is equal to, okay, now if we integrate the x squared, we'll get x cubed over 3. Remember, raise the exponent by 1 and then divide it by that new exponent. And then we can include a plus c. You only have to include that once because there's no point in putting two separate constants. Okay, so now this is just going to solve for y. So to solve for y, we will take everything and, I don't know how to really say it, like put it as the power to the base of e or whatever. I don't know how to say it, but you're going to put base of e and then these are going to be the exponents. So if we do this, the e and the natural log are going to cancel out. And then that's going to leave us y minus 1. And this is going to just get us e to the x cubed over 3 plus c. And let's use a bit of algebra here. E to the x cubed over 3 plus c, if we split this up into two different exponents, we'll get e to the x cubed over 3, and then we'll get e to the c, right? Because if you have two exponents in the same base, it's like you're adding the exponents. So we kind of undid that property here. And then, so let's take a closer look at this e to the c. This is just a constant, right? E is a constant and c is a constant. So instead of having as e to the c, we can just replace this with just c, because it's just some constant number. I don't know what that number is, but it is some number. Okay, so if we simplify this a bit further, we'll get y minus 1 is c times e to the x cubed over 3. And I just want to make clear that this c here and this c here are obviously two separate numbers, but we don't care what the actual value of them is. We just want to make sure that there is some constant. That's all. Okay, and then I'll just add 1 to both sides to solve for y. Y is equal to c e to the x cubed over 3 plus 1, like so. So, but we're not quite done yet because we need to use our initial condition to figure out the value of c. So we know that in this equation, if x is 0, y is 3, right? So now we're going to plug in our point. We will plug in 0, 3, and that's going to get us, so 3 equals c times e to the 0 cubed over 3, 0, plus 1. Right, I just plugged in 3 for y and 0 for x. So this gives us 3 equals, okay, e to the 0 is 1, so c plus 1. So c is equal to 2, right? So that means in this initial equation here, y is equal to c e to the x cubed over 3 plus 1. Since c is 2, I can replace it with a 2. So we'll get 2 to the x cubed over 3 plus 1. And that is our final equation. That's our final f of x. Wow, okay, so this was a 6-point question. That's why I love these differential equation questions. They're just so chock full of points. So we got 1 point for successfully separating the variables like this. 1 point, or wait, no, it's 2 points for performing the integration correctly. I guess I want to give you 1 point per, but it's not clear if it's 1 point for each or just 2 points for them both in total. So you get 2 points for successfully performing the integration, 1 point for having a mention of plus c, another point for using your initial condition here to find the value of c, and then another point for finding the full final answer that's correct. those 6 points. That was the end of question 6, end of 2004 AP Calculus AB. Hope you found this video helpful, and I will see you in the next one. Goodbye.